It begins in a place that feels familiar. A quiet sky, steady patterns, motion that repeats without surprise. If you watch long enough, the system reveals itself. Inner worlds, small, dense, built of rock and metal, circle close to the star. Beyond them, larger planets take shape, wrapped in thick layers of gas, moving along wide, gentle paths. Nothing seems out of place. Nothing resists explanation, and the explanation itself is satisfying. Near a star, heat is intense. Only heavy materials endure. Farther out, where temperatures fall, lighter gases can gather and grow into massive planets. Around a young star, a disk of dust and gas slowly organizes. Particles collide, combine, and settle. Over time, a structure emerges that feels almost inevitable. The more you look, the more it holds together. There is a certain comfort in this kind of order. It suggests that the universe is not only understandable, but predictable. If one system behaves this way, perhaps all systems do, the pattern begins to feel less like an observation and more like a rule. For years, astronomy rested in that quiet confidence. Then, in 1995, a measurement introduced a small disturbance. A star, 51 Pegasi, showed a subtle repeating motion. The cause was inferred, a planet, unseen, exerting a gravitational pull. This was expected. What mattered was the orbit. When calculated, it did not align. The planet, 51 Pegasi b, was not distant and cold. It was extremely close to its star. Its year lasted just over 4 days. Compare this with Mercury, which takes 88 days to orbit the Sun. This is not a variation. It is a different arrangement entirely. At such proximity, temperatures exceed 1,000 degrees Celsius. Under the framework that had seemed reliable, a gas giant could not form there. The conditions oppose the process, and yet the planet is there, massive, stable, undeniable. That single contradiction carried deeper details. 51 Pegasi b orbits at about 0.05 astronomical units, nearly 20 times closer to its star than Earth is to the Sun. Its upper atmosphere likely reaches between 1,000 degrees Celsius and 1,500 degrees Celsius, causing expansion and gradual loss of lighter gases into space. It is also almost certainly tidally locked. One side faces the star continuously, while the other remains in darkness, creating extreme temperature differences across the planet. Its orbit is nearly perfectly circular, shaped over time by tidal forces that smooth out irregular motion. And unlike Jupiter, it is unlikely to host stable moons. The star's gravity would disrupt any such system. What makes this discovery even more significant is how it was made. Astronomers did not see the planet directly. They detected a tiny wobble in the star's motion. From that small signal, they calculated the planet's presence, mass, and orbit. Here is the key teaching insight. In science, we often understand reality not by seeing it directly, but by carefully measuring its effects. 51 Pegasi b became the first of what we now call hot Jupiters. Today, many such planets are known. But this was the first clear sign that planetary systems do not follow a single pattern. The sky, once seen as orderly and predictable, revealed something else. Not disorder, but possibility. And with that, the search changes direction. No longer toward confirming what we expect, but toward discovering what we have not yet imagined. Once that first contradiction is accepted, the search changes direction. Astronomers no longer look for systems that confirm expectations. Instead, they begin to notice patterns in what does not fit. And with improved detection methods, a new category of worlds starts to emerge. Planets defined not by stability, but by extremes. One such example is WASP-76b. On the side facing its star, temperatures exceed 2,400 degrees Celsius. At this level, we are no longer discussing weather in any familiar sense. Materials that are solid on Earth do not remain solid there. This planet is tidally locked. One side constantly faces the star, absorbing continuous energy, while the other remains in darkness. The result is a severe temperature imbalance across the planet, and nature responds to imbalance with motion. Winds on WASP-76b are estimated to reach speeds of around 18,000 kilometers per hour. To place that in perspective, The fastest winds on Earth barely exceed 400 kilometers per hour. These are not storms, they are global atmospheric flows driven by extreme physics. Under such conditions, iron does not remain solid. It vaporizes. The intense winds carry this vapor across the planet from the hot day side to the cooler night side. As temperatures drop, the iron condenses, and then it falls, not as water, as liquid metal. This is not a theoretical model. It is based on observational data that shows signatures of iron in different states across the planet. Another planet, HD 189733b, presents a different form of intensity. Its winds reach speeds of about 7,000 kilometers per hour. But what they carry is even more revealing. The atmosphere contains vaporized silicate particles, the same basic material found in sand and glass. As these particles cool, they condense into tiny shards. The result is rain composed of glass. And because of the wind speeds, this rain does not fall vertically. It moves sideways, driven at supersonic speeds across the planet's atmosphere. Here is the teaching insight to take from this. Atmospheric behavior is not universal. It depends entirely on local conditions. Change the temperature, pressure, and composition, and what we call weather becomes something fundamentally different. These planets are not isolated anomalies. They represent a broader class of worlds shaped by extreme proximity to their stars. And this raises a more important question. If heat alone can transform a planet so completely, then what happens under entirely different conditions, where the problem is not survival, but stability itself? If extreme heat can reshape a planet's atmosphere, the next question is more unsettling. What happens when a planet cannot hold itself together at all? There are worlds where stability is not guaranteed, where existence itself becomes temporary. One such example is WASP-12b. This planet orbits extremely close to its star, even closer than many of the hot Jupiters we have already discussed. At such distances, gravity is no longer a simple force holding things in place. It becomes uneven. The side of the planet facing the star experiences a much stronger gravitational pull than the far side. This difference creates what we call tidal forces. On Earth, tidal forces from the Moon cause ocean tides, but on WASP-12b the effect is far more extreme. The planet is being stretched. Instead of maintaining a nearly spherical shape, it is pulled into an elongated form, almost like a droplet being drawn outward. This distortion is not just a surface effect, it influences the entire structure of the planet. At the same time, its atmosphere is no longer stable. The intense heat and gravitational stress cause the outer layers to expand. Once these layers extend far enough, they are no longer held by the planet's gravity. They escape. Observations show that material from WASP-12b is actively flowing away from the planet and toward its star. This is not speculation. It is directly measured through changes in light and spectral signatures. Over time, this process will continue. Scientists estimate that the planet has only about 3 million years remaining before it is completely consumed. In cosmic terms, this is a very short lifespan. Here is the teaching insight to consider. We often think of planets as stable, long-lasting objects, but stability depends on balance. When forces become too extreme, that balance breaks and even large planets begin to disappear. WASP-12b shows us that planetary systems are not fixed structures. They evolve and sometimes they decay. This leads to a broader realization. Not every planet we observe represents a stable endpoint. Some are being observed in the final stages of their existence, and this raises a deeper question. If planets can be stretched, stripped, and eventually destroyed, then what other forms might exist? Worlds that are not just changing, but fundamentally different from anything we expect. If destruction shows us that planets can lose their structure, the next step is more subtle. Not all extremes are violent. Some are quiet, yet just as revealing. Consider how a planet interacts with light. On Earth, we take this for granted. Clouds reflect sunlight, oceans absorb it, and the balance between the two shapes our climate. But beyond our solar system, this balance can shift in ways that seem almost counterintuitive. One such example is TRES-2b. It is known as the darkest planet ever discovered. It reflects less than 1% of the light that reaches it. To put that in perspective, it is darker than coal, darker than most materials found naturally on Earth. This is not because it lacks an atmosphere. In fact, its atmosphere likely contains elements such as sodium and titanium oxide, which absorb incoming light very efficiently. Instead of reflecting energy, the planet traps it. If you were able to observe it directly, it would appear as a faint silhouette, barely distinguishable even when illuminated by its star. Now consider the opposite case. LTT9779b reflects nearly 80% of the light that reaches it. Its atmosphere contains clouds made of silicates and metallic compounds. These particles act like tiny mirrors, scattering light in all directions. The result is a planet that appears unusually bright, despite being extremely close to its star. Instead of absorbing energy, it reflects a large portion of it back into space. These two planets represent extremes of what we call albedo, the measure of how much light a surface reflects. One absorbs almost everything, the other reflects nearly everything. Here is the teaching insight. A planet's appearance is not determined by its size or distance alone. It is shaped by the chemistry and structure of its atmosphere. Change the composition, and you change how the planet interacts with light. This introduces a deeper realization. Even something as fundamental as brightness, what we might assume to be simple, is controlled by processes that vary from planet to planet. And this leads us forward. If appearance itself can differ so dramatically, then the question is no longer just how planets behave, but what they are actually made of. If light can mislead us about how a planet appears, the next question moves deeper. What is a planet actually made of when conditions are pushed beyond anything we experience locally? Until recently, composition seemed straightforward. Planets were either rocky like Earth or gaseous like Jupiter. The distinction felt clear, almost complete. But as new observations accumulated, this boundary began to blur. One of the most discussed examples is 55 Cancri e. This planet orbits very close to its star and experiences extreme temperatures. Under such conditions, its internal structure does not behave like that of Earth. Based on early analysis, scientists proposed that it could be rich in carbon. Now consider what that implies. Under immense pressure, carbon does not remain in familiar forms. It transforms. One of those forms is diamond. Calculations suggested that a significant fraction of this planet's mass, possibly up to 1/3, could exist as crystalline carbon. This is not a decorative idea, it follows directly from physics. Change the chemical composition and apply sufficient pressure, and entirely different materials emerge. However, further studies introduced an alternative interpretation. Instead of being carbon-dominated, the planet may contain large amounts of aluminum oxide. In such a case, its interior would resemble materials like sapphire rather than diamond. At first glance, these possibilities may seem speculative, but the underlying principle is solid. Here is the teaching insight. A planet's composition is not chosen randomly. It is determined by the chemistry of the star it forms around. The elements available in the protoplanetary disk define what the planet can become. This means that if a star contains a higher proportion of carbon relative to oxygen, the planets forming around it may be fundamentally different from those in our solar system. The same applies to other elements. A simple comparison can help. Imagine baking with different ingredients. Even if the process is the same, the final result depends entirely on what you start with. In planetary formation, the ingredients are set by stellar chemistry. 55 Cancri e demonstrates that planets are not limited to Earth-like compositions. They can be built from entirely different material frameworks, leading to structures we do not encounter naturally. And this extends the question further. If composition itself can vary so dramatically, then structure may not follow the patterns we expect either. Some planets may not just be different in material, but in how that material is arranged and sustained over time. If composition can vary so dramatically, the next question becomes unavoidable. What happens when the very density of a planet no longer follows any familiar rule? Until recently, size and mass were expected to scale together in predictable ways. Larger planets were assumed to be heavier, with strong gravity compressing their interiors. But new observations have revealed a category of planets where this relationship breaks down. The Kepler-51 system provides one of the clearest examples. Here, astronomers discovered planets that are roughly similar in size to Jupiter, yet their masses are only a few times that of Earth. This creates an unusual situation. A large volume combined with very little mass results in extremely low density. In fact, these planets are less dense than styrofoam. To understand this, imagine two objects of the same size. One is solid rock, the other is mostly empty space filled with light gas. The difference in weight is significant. The Kepler-51 planets resemble the latter case on a planetary scale. Their structure is dominated by thick atmospheres composed primarily of hydrogen and helium. These gases expand under heat, creating a swollen, inflated appearance. The result is a planet that looks massive, but is physically very light. This raises an important point about perception. Size alone does not determine a planet's nature. Without knowing its mass, we could easily misinterpret what we are observing. Here is the teaching insight. Density is one of the most important properties in planetary science. It tells us how matter is distributed inside a planet, and often reveals more than size or appearance alone. There are still open questions about these superpuffs. One possibility is that they are young planets. Over time, stellar radiation may strip away their outer layers, gradually reducing their size. Another possibility is that they represent a stable class of planets that simply form under specific conditions. Either way, they challenge a basic assumption that planets must become more compact as they grow larger, and this leads us forward. If even something as fundamental as density can vary so widely, then the next layer of complexity lies not in what planets are made of, but in how they move. Because motion, too, may not follow the patterns we expect. If structure and density can diverge so dramatically, then motion becomes the next layer where expectations begin to fail. Until recently, planetary orbits were assumed to be relatively simple. Nearly circular paths stable over long periods moving in the same direction as the star's rotation. This was not just observation, it was treated as a natural outcome of formation. But some systems do not preserve that simplicity. Consider HR 5183b. For most of its orbit, this planet remains far from its star, moving slowly through the outer regions of its system. Then, over a short interval, it accelerates dramatically, sweeping inward before moving back out again. Its path is not circular, it is highly elongated. To understand this, imagine a pendulum that spends most of its time near the edges of its swing, then rapidly passes through the center. The motion is uneven, stretched over distance and compressed in time. This type of orbit is described as eccentric. In the case of HR 5183b, the eccentricity is extreme, but the deviation does not end there. In many planetary systems, planets orbit in the same direction as their star rotates. This alignment reflects their shared origin in a rotating disk. However, some planets move in the opposite direction. This is known as retrograde motion. Such behavior suggests a past that was not stable. Gravitational interactions, collisions, close encounters, or the influence of other massive bodies can disrupt original orbits. Over time, these interactions reshape the system, creating paths that no longer resemble their initial configuration. Another example, TIC 241-249530b, takes this even further. Its eccentricity is measured at approximately 0.94. To interpret this, consider that an eccentricity of 0 represents a perfect circle. A value close to 1 approaches a straight line. This planet's orbit is stretched to such an extent that it nearly behaves like a long, narrow trajectory, rather than a loop. Here is the teaching insight. Orbital motion is not just a result of formation. It is a record of everything that has happened to a system over time. Each irregularity carries information about past interactions. These planets show that planetary systems can experience periods of instability, where gravitational forces rearrange their structure. The result is motion that appears chaotic, but follows precise physical laws. And this leads us to a broader realization. If orbits themselves can become so extreme, then planets are not always bound in the way we expect. Some may not remain tied to any star at all. If motion itself can become unstable, the next possibility is more fundamental. What if a planet is no longer bound to any star at all? In our earlier understanding, a planet was defined by its orbit. It formed around a star and remained gravitationally tied to it. That relationship seemed essential. Remove the star, and the system should collapse. But observations have revealed a different reality. There exist planets that drift freely through space. They do not orbit any star. They move through the galaxy alone. These are known as rogue planets. At first, this idea appears counterintuitive. Without a star, a planet receives no continuous source of light or heat. It becomes cold, dark, and difficult to detect. And yet, evidence suggests that such planets are not rare exceptions. Using advanced instruments such as the James Webb Space Telescope, astronomers have identified hundreds of these objects in regions like the Orion Nebula. Some of them even exist in pairs, orbiting each other while traveling through interstellar space. This is a significant shift in perspective. A planet no longer requires a star to exist. It only requires sufficient mass and a history that allows it to form or be ejected. There are two primary ways these rogue planets may originate. Some likely formed within planetary systems and were later expelled due to gravitational interactions. Close encounters with other massive bodies can provide enough energy to push a planet out of its system entirely. Others may form directly from collapsing gas clouds, similar to stars, but without gaining enough mass to ignite nuclear fusion. In this case, they are not ejected. They are born isolated. Here is the teaching insight. Definitions in science are often shaped by initial observations. As new evidence emerges, those definitions must expand. A planet is no longer defined only by its orbit, but by its physical properties and origin. Estimates suggest that there may be billions of rogue planets in our galaxy, possibly even outnumbering stars. This implies that a large portion of planetary objects exist in environments we rarely consider. These worlds are extremely difficult to observe. They emit little to no visible light. Detection often relies on indirect methods such as gravitational lensing or faint infrared signals, and this leads to a deeper realization. Planetary systems are not closed structures. They can lose members. They can rearrange. They can produce objects that continue to exist independently of any star. Which brings us to the next question. If planets can exist without stars, then what happens when the star itself is no longer alive? If planets can exist without stars, the next idea seems even more difficult to accept. What if planets can form after a star has already died? For a long time, planetary formation was understood as a process tied directly to the birth of a star. A star forms, a disk surrounds it, and from that disk, planets emerge. The sequence felt fixed, almost chronological, but in 1992 observations revealed something unexpected. The first confirmed exoplanets were not found around a sun-like star. They were discovered orbiting a pulsar, a neutron star formed after a supernova explosion. This is not a gentle environment. It is the remnant of a violent stellar death, where intense radiation and shock waves would destroy any nearby structure. This immediately raises a logical problem. If a star explodes as a supernova, any pre-existing planets should be destroyed or ejected. The energy released is sufficient to disrupt entire planetary systems. So how can planets exist in such a location? The answer lies not in survival, but in formation. These planets did not survive the explosion. They formed after it. Following a supernova, some material remains bound to the collapsed core. Over time, this debris can settle into a disk, similar in structure to the disks around young stars. From this disk, new planets can emerge. This process is known as second-generation planetary formation. Here is the teaching insight. Formation is not limited to beginnings. Under the right conditions, structure can emerge even after destruction. The same physical principles, gravity, collision, accumulation, apply again, but in a completely different context. However, these planets exist in extreme environments. Pulsars emit intense radiation, including high-energy particles and electromagnetic waves. Any nearby planet is exposed to conditions far beyond what we consider habitable. This changes how we think about planetary systems. A planet is no longer just a product of stellar birth. It can also be a product of stellar death. The timeline is not linear. It can reset and begin again. And this leads us forward. If planets can form in such unexpected ways, then the question is no longer just where they exist, but whether our current models are capable of explaining all the systems we continue to discover. If planets can form after destruction, then the final question is unavoidable. How complete is our understanding of planetary systems today? At this stage, it is tempting to believe that we have seen enough variation to understand the full range of possibilities, but recent discoveries suggest otherwise. Instead of closing gaps, each new observation seems to open them further. Consider TOI 6894b. This is a giant planet orbiting a small red dwarf star. Based on current formation models, such a pairing should not occur. A star of that size is not expected to host a planet of such mass. The available material in its protoplanetary disk should be insufficient to build it, and yet the planet exists. A similar challenge appears with LHS 3154b. Here, the mass of the planet is unusually large compared to its host star. The ratio does not align with established models of planetary formation. Once again, the observation is clear, but the explanation is not. These are not isolated anomalies. They represent a growing pattern. As of now, more than 6,000 exoplanets have been confirmed. This is a significant number, but it comes with an important limitation. The methods we use to detect planets are biased. We are more likely to find large planets, planets close to their stars, or planets that produce strong, measurable signals. This means that what we currently observe may not represent the typical planetary system. It may represent the easiest systems to detect. Here is the teaching insight. In science, observation is shaped by the tools we use. If the tools favor certain outcomes, our understanding may also be skewed toward those outcomes. This leads to a careful conclusion. Our models are not incorrect. They are incomplete in ways that are still being uncovered. Each new discovery does not simply add information. It tests the boundaries of what we believe to be possible. The universe does not adjust itself to match our expectations. It reveals patterns gradually, often through exceptions. And perhaps the most important realization is this. What we currently describe as unusual may, in time, become ordinary. And what we consider ordinary may simply be what we have been able to observe so far. So the question is no longer how many planets we have discovered. The question is how many kinds of planets we have not yet seen. Because at this stage, one thing is clear. What we have discovered is only the beginning.